Last day of the conference, right? All these smiling, chipper faces, like thinking about getting home, I'm sure. Well, thank you for showing up. It's great to see everybody. I recognize some faces from the last couple of days, so thank you for coming out. Couple of things. I've got 3 questions I want to ask the audience this morning to kind of get you thinking about what our keynote speaker, Jeff Hopper, is going to be talking about. Just a quick show of hands. Who here is in charge of managing the sizing and management of an Asterisk platform? Can I see a show of hands? Okay. Okay, very good. Second question, how large are those Asterisk environments? For example, 1 to 5 servers? More than 5? Okay, very good. Thank you. And then the last question, how many of you that are managing those are managing voice applications on that platform? Okay, great, thank you. So sizing and management becomes more complex as companies are moving away from individual premise-based environments and moving toward large enterprise environments. So in today's session, our VP of Client Services, Jeff Hopper, is going to address those issues, as well as some special other considerations that need to be addressed in the multi-tenant and multi-application environments. Before we bring Jeff up, just real quick, we will have a drawing at the end of today's presentation. So if you we haven't collected your card, make sure we get it. Got a couple of nice parting gifts, if you will. So without further ado, VP of Client Services, Jeff Hopper.
Thank you. Thanks, Brooke. Good morning, everyone. We have a lot of ground to cover in 44 minutes, 43 minutes and a half, because I know we're on a really tight timeline, so I'm going to jump right in. What I wanted to talk to you about this morning is really how the world has changed from when I was a kid, when we started with Asterisk servers, and I'm getting a lot of feedback there, to today, when most everything was 1 or 2 server, small premise installations. And now we find ourselves in a world, especially over the last 4 or 5 years, with the evolution of cloud computing and multi-tenant hosted situations for voice platforms, where we have customers, in our case at MLBox, I've got customers with as many as 2,000 ports of speech recognition operating in a cluster of servers. And that's a very different world than 4 ports on a single server in the back office handling phone calls and the phone tree in a small business. And in the process of doing that, I've been the lead for our technical team at figuring out how to make that work, frankly. Scaling all the problems that were anticipated or unanticipated from these larger environments. So what I want to do over the course of the session, and I hit the wrong button on the laptop, sorry, is give you some contact information. This will be in the slide deck. But it's real easy if you have a follow-up question or want to talk some more about it, jeff@lumenvox.com. That's pretty straight up to remember, and I know they're going to have this slide deck available for you afterwards. Also, I want you to know the other 2 compatriots I have here with me that deal with our Asterisk customer base from a speech recognition and voice biometrics perspective. Brooke Fritz is an account manager that introduced me, and Kevin Connolly in the back of the room is somebody I think a lot of you may have talked to in your business interactions with us, but they're our Asterisk specialists. I also want to give you one quick 2-slide plug for MLBox, if you'll indulge me for just a half minute or so. Many of you know MLBox because we've traditionally been the default speech recognition engine in the Asterisk community. We've recently made an acquisition of a company named VoiceTrust that's based out of Munich, Germany. And it's added some significant new products to our portfolio. We now have a set of voice biometric engines to do things like authentication for entry into a contact center or an IVR application, password resets, and other things where voice biometrics, face biometrics, or multi-factor authentication may be applicable to your application stack. So our list of things, you can see on here all the stuff that we have, has grown quite a bit. Keep us in mind for those elements and the fact that we're now a much more global company with support and development centers both in Munich and in San Diego and offices around the U.S. We've also added not just core technology like our speech recognition engines and text-to-speech. We now have some application layer functionality that you can deploy also. So we have our traditional core technologies in the blue boxes down at the bottom, ASR, text-to-speech, call progress analysis, and the tuner. We also have both passive and active biometrics engines that can do face recognition, voice biometrics, and very shortly we'll also have fingerprint capabilities to go into the engine, and a set of applications on top of that for password reset, proof of life, authenticating into a call center, and multi-factor authentication, even for logging into desktop computers or through mobile frameworks. So, end of the infomercial. Let's get to the real agenda that you came here to hear about. I'm talking about creating super scalable speech deployments in an Asterisk world, and there's some very specific considerations that come with scaling beyond a single box or a small cluster of boxes that, frankly, we've experienced growing with some of our large clients over the last few years. I think we have a total of about 12 customers that have larger than 1,000 port deployments. Probably a third of those are deployed in the AWS cloud, completely outside of their own data center. The others are in their own data centers, but they're really large deployments. So we've been to the University of Hard Knocks, and we've learned some things and engineered some things into our product and worked out some of the questions that come from that. And those really fall into two layers. The first one is the physical architecture. How do you make all these things talk to one another? How do you distribute the work and the software components? And then the second piece are the logic components of this. Issues around single or multiple tenancy and shared resources, and around the different kinds of applications that you'll have in a really heterogeneous mix of things running on the same platform. And then a few other sidebar learnings that we figured out of this. So, from my perspective, I remember back to the point that lots of folks in the Asterisk and other open source communities were building single-purpose IVRs with an Asterisk box and dial plan that set in a business. They were typically very small deployments, 4, 8, 12, up to the point of a T1 card, essentially was about the max. And it was all traditional TDM telephony. And we've grown, beginning about 15 years ago, MLBox jumped into this space and started providing speech recognition for the environment so that you could do more than just dial plan and DTMF for your customers. And now we've reached the point, as I said, where we have these multi-thousand port deployments supporting hundreds of different customer applications running in the same environment. And that seems to be the trend. I think more and more people who come to us to build applications and deploy speech recognition, text-to-speech, and voice biometrics really are focused in this building a big platform space so that they can offer those as a platform as a service or software as a service to the rest of the world. So the first part I want to talk about is the physical. And I want to set a little bit of a background just in case everybody in the room isn't on the same page. There are really a set of components that go into a speech-based self-service application in this environment. Obviously, you need an Asterisk server. You're going to write application logic either in dial plan or come into the Asterisk server through the Asterisk gateway interface with PHP or other kinds of application code. The second piece that builds on that for any speech recognition or text-to-speech use is the need for what's called an MRCP stack or gateway. I think, how many of you are familiar with Uni MRCP? Is that something the room's pretty, couple of people, not a lot. The thing to understand there is that pretty much every speech product in the world, MLBox or others, you talk to it using an MRCP interface, which is a messaging protocol that's transported over TCP/IP, and your voice application platform, in this case Asterisk, needs to be able to send MRCP-based instructions to the speech platform. And that's not native to Asterisk. There is a great open source project called Uni MRCP, and it's at the .org address, that provides that bolt-on piece of technology so that an Asterisk application, when it requests speech recognition or text-to-speech synthesis, can translate those instructions into MRCP messaging and can be configured to know where the speech servers are or the text-to-speech servers to send that instruction and how to get the response. The third piece that we're finding more and more common is the need for some kind of either physical or logical load balancing. Because one of the downsides of Asterisk technology today, and I'm sure this limitation will go away eventually, but it hasn't yet, is that the UniMRCP stack can only know about one MRCP resource at a time. So it can only have the IP address for a single speech server or a single text-to-speech server. And as a result, you've got a scaling problem already if you're trying to grow the platform, because it can't distribute work across more than one, either for failover purposes or in an N+1 model where you've got N being the number of servers you need for your capacity and then an additional one for redundancy in case you have a hardware component fail. So load balancing is a critical piece of building large Asterisk-based speech implementations these days. And then over on the speech product side, what you typically find are 4 components. There's a media server of some kind that essentially is the MRCP receiver on the speech side. It takes the messages that come from Asterisk and UniMRCP and deploys the tasks and returns the results. But it acts as a traffic cop for that MRCP messaging. You'll usually also find in most of the products in the industry today, there's a license server of some kind that sits there and knows how many simultaneous ports of speech recognition or text-to-speech and in what languages or voices you have licenses for, and the tier of recognition and all the dimensions that go to speech licensing. And then there's usually an ASR engine itself over and above the MRCP media server and the license server, plus language models for each of the languages you support, things like French Canadian, North American English, North American Spanish, Brazilian Portuguese, I think someone asked about. So most of these engines, including ours, support dozens of languages that can be recognized in. And then a text-to-speech engine and voice packages for each of the voices you use in case you have male or female, English or French or Portuguese languages, things like that. So all of those pieces, you have to figure out how many of each, the capacity of each, and how to get them all to talk together. And that's really the trick of these large environments. In a typical, what I'll call a back in the day deployment, you usually saw 3 servers involved in this process, although sometimes all of this stuff would get put on a single physical box. There's an Asterisk server with an instance of Asterisk and UniMRCP on it to create the gateway to the other services. There's almost always an application server that sets off to the side somewhere with either databases or HTTP-based code that you'll use in the application for your grammar for the speech engine or other things. And then a speech server that has those 4 speech components that I described that sit on there. The app servers are usually HTTP-based or occasionally a direct API into a database, and then all of the traffic to the speech servers are done using MRCP, which is simply a messaging protocol. It actually stands for Media Resource Control Protocol. It's an RFIC standard. So the first problem we get into, as I mentioned, is that in scaling these, an Asterisk server in UniMRCP can only talk to one target. It can't be configured to know I've got 2 or 3 or 4 speech servers or other resources out there that it might use. So one approach to solving the problem, a physical load balancer. You're all familiar with those from your data centers. They tend to be somewhat expensive appliances, and they're in many ways a little bit of art and voodoo involved in configuring them to work correctly. Not that it's impossible, but it's an extra step of complication and expense in most cases, but one that a lot of people use to solve the problem, so that then you can have multiple speech servers, usually containing the entire speech stack on them at the back end. I see that as the route that many people start with, but I don't see it as the route that most people end with, frankly, when we work through larger configurations, because of the complications of having an extra piece of single point of failure and a load balancer in the middle, and just learning to use them effectively in the environment. So, excuse me. So what we see more people doing today, and it clearly goes to the capability of individual products, and I'm going to do one of these just a bit for LumenVox. We've done a lot of engineering to create ways to avoid that load balancer problem in the middle by taking on some of the work in the speech stack. So if you can picture this model, you can have actually multiple speech servers that set out there and get requests from multiple Asterisk servers. But those speech servers, you'll notice in this model, don't have the ASR and the text-to-speech on board on the same box. Since almost everybody who builds large data centers today deploys using virtualization, and let me do another one of those show of hands questions. How many of you virtualize almost all your servers in this kind of environment? Yeah, pretty much everybody in the world. That gives us the ability to do some things where you didn't want to put up 15 boxes, but it's really pretty easy to put up 15 virtual servers, on two or physical host or whatever your physical host environment is. So with the LumenVox stack, what you can do in one model is to just put the media servers and the license servers on what I call a row of servers in front of your Asterisk stacks. And then our media server can literally do workload distribution to an identified list of ASR or text-to-speech servers that sit in the background. There are some other vendors evolving this. I think we're the first one to market with it at this point, but I believe it'll become the de facto way to do these kind of large-scale deployments because you can segregate tasks so that it's just the media server running on one logical server or a series of them, and the same thing for text-to-speech and speech recognition servers. And the advantage there are multiple. You can have lots of cookie-cutter copies of things that work exactly the same way, and you understand how to size them just for one task, whether it's memory or CPU utilization. And you can configure them through their config files so that each media server knows about every ASR that's available. Our media server actually communicates in a unitary thread with each of those that's in its config list and says, are you there? How busy are you? Are you there? How busy are you? To each of those servers. And then when it gets a work request from MRCP, it goes, this server is the least busy right now. I'm going to send the request over there. Or, oh, this one's really busy. No, don't do that. I'll use this one. So we actually have a workload algorithm in place at the media server level that evaluates the response times that are currently occurring and have occurred over the last few minutes from each of the ASR servers and each of the TTS servers that sit in the background so that it can distribute work for you. You don't have to manage that task, and it doesn't require a hardware-based load balancer or anything to set in the middle. The one other approach I've seen customers use, and there are mixed pros and cons for it, but it's worth mentioning, is to actually take our media server and set it on the box with Asterisk and with MRCP so that you have those three elements setting in the same server. They become a unitary point of failure, but if you've got multiple Asterisk servers, if you lose one of those, you can still distribute traffic to the Asterisk servers, and then there's literally no workload distribution you have to manage other than at the front end of calls into your Asterisk environment. Does that make sense so far? Is this resonating with you guys just a bit? So essentially, from a distributed architecture perspective, there are two main models I tell people to look at. Use a physical or logical load balancer between the Asterisk platforms and your speech recognition environment, or use Asterisk, MRCP, and the media server all in the same box, and then let the media servers distribute work to a distributed set of ASR and TTS resources that sit in the background and handle all of the workload. The really nice thing you can do there too is from a hardware and software management perspective, if you have really good monitoring, and in our case we have a very rich SNMP implementation in our products, it can literally alert you that this whole server is like running at 90% memory or 90% CPU. And you can do things like spin up an additional logical server that's already pre-configured with an IP address automatically to distribute additional workload to. For our customers who are deploying in the AWS cloud, that's a very common model to add or eliminate servers on demand in real time based on the traffic that they have in the environment so that you're not paying for extra computational capacity, in a publicly hosted cloud like that. Questions so far? Make sure I'm Doing good here, time-wise. The next thing to talk about is the issue of single or multiple tenancy. And there's some things that, again, are learning experience from us and our customers. If you've written any speech applications or you've been around them, they're really odd beasts sometimes to size the right amount of hardware resource computationally, because there are wide variations in how much CPU or memory you need based on the actual request. And I'll give you an example. If you're recognizing first and last names in an application from somebody, the grammars or the list of names that can be recognized for North America can be up in the 20, 30, 40,000 entries. Every time you make a recognition request, the recognizer pulls that grammar in, creates this in-memory model, search model with that list of words and all the possible phonetic combinations, and then passes the audio against it. When you do that, depending on the size of the grammar and the number of permutations and complexity, I might drop them there, that can be a really big piece of memory. It can be a 3 or 4 meg or 5 megabyte chunk of memory, whereas a yes-no menu might be a few hundred kilobytes of memory. So the actual context of each of the requests that come in, or the text-to-speech synthesis. In some cases, you might synthesize a short prompt for the IVR. Please tell me what topping you'd like on your pizza. Or in some cases, we've got people who read long paragraphs of disclosure information or news readers or things like that. And it takes more horsepower computationally to synthesize a 3-paragraph piece of audio back into an application than it does a 4-word or 5-word sentence. So scaling these things is art plus computational science. It's why I recommend profiling the load under an actual customer environment and using things like either the native tools in the AWS environment if you're there, or things like our SNMP monitoring alert messaging, so that you know when the servers are low, medium, or high utilization, and you can track that over time and see exactly what kind of demand your mix of customers and applications has on the servers. And the nice thing in a virtual world is that you can simply recast those. You can say, okay, I started this up as a 4-core, 16 gigabyte machine with reserved memory and CPU, but I'm taxing it to like 90% in that model. Let me just recycle that machine, bring up one that's configured as 8-core and 32 gig of memory, and have a more robust server from a virtual perspective very quickly in the world. So you have to be very mindful of looking at real production load and monitoring it over time to see what the behavior's like in a contact center when you have lots of different applications, each have their own calling patterns, each have their own variables in them, so that you can size those correctly. There's also a thing, how many of you are familiar with the concept of tuning a speech application? Anybody? Looks like that might be an alien term. Speech applications, as I always say, require care and feeding or tuning, because you've all called something and the application went, I'm sorry, I didn't understand you, or you had a bad recognition result. And it can be application logic problems, it can be the grammar that I described, that search space that's designed might not have all of the terms in it or the right weighting on the terms in it, but there are things that involve linguistic art in a speech app that you need to tune away the problems. And to tune them, you typically capture real call audio and the recognition results in the form of log data. For us, we call it a call SRE file, so every call has a little blob of data that can be written to disk. In a big multi-tenant platform where you have thousands of callers and tens or hundreds of applications, those log files can get to be immense and become a really difficult problem. I actually call it searching for a needle in a haystack sometimes. If you want to tune one piece of one particular application, trying to filter your way through 100,000 calls that occurred yesterday can be a nightmare. So one of the things that we've done, and I find more and more speech engines are implementing, is the ability to selectively log that extra heavy logging data that you need for a tuning exercise. The W3C spec for MRCP messaging supports what are called vendor-specific parameters. And you can put a message in a grammar header that says, when you're processing this grammar, go to high-level logging. In that case, we've just set up some logging instructions as vendor-specific parameters. So you don't have to turn logging on for every call on 100 servers in order to capture the specific data you need to look at a specific application. You can simply insert some code into your application code or the grammars for that application that says, when you get this particular dialog state, I want to log it so that I can do tuning with it. It also allows you to put in tags that are just identifiers that you can use that are embedded in that data. And then with our speech tuning tool, you can import that data from your production platform for a tuning exercise, pull all those files in, use some drop-down filters and go, I want all the ones that have the tag X, and use the grammar R. And then you're down to a clean list really quickly and easily to tune rather than filtering through what in some cases I've seen can be terabytes or at least lots of gigs of audio data and log files that you're trying to find information in. A couple of other considerations that I think are universal in the speech recognition industry but not well recognized. When people set up multi-tenant platforms, they tend to want to offer lots of languages and lots of different text-to-speech voices for their end customers to use so that they have a wide selection. I don't think there's a single recognizer in the world today that supports having more than 4 language models on a given server physically, because each of those language models takes up a chunk of memory and takes time to cycle in and out based on the requests. So when you design your application infrastructure, you want to keep in mind, don't ever put more than 4 text-to-speech voices or languages on any given server. And I think that's pretty universal across all the speech vendors I know, which means up front you may need to do some segregation of traffic in your Asterisk stack and send the Spanish-speaking customers or the Brazilian Portuguese customers to one set of servers and send the US English to another set of servers if you're going to need more than the 4. Now, the good news is you can support the Americas easily with 4 languages, with Canadian English, Spanish, and Brazilian Portuguese. You got all of North Pole to Terra del Fuego covered. But if you're somewhere else in the world and you need more language options, it's certainly something you want to keep in mind as you design your applications. I've already mentioned the sizing topic, so I think we've hit that mostly. Another consideration, especially in a multi-tenant platform, is protecting data privacy. And that's a concern for everybody these days, especially if you're processing credit card transactions or other financial transactions, or you're doing healthcare information where there's HIPAA compliance issues in it. You want to plan on and make sure that your vendor, whoever they are for speech engines, supports log masking, so that when you're collecting logging data from an application and the recognition results, you either mask or encrypt specific data that you don't want to be visible to anybody. In our case, we support both log masking selectively, so you can turn it on in the point in a call where you're collecting a credit card information, for instance, and then turn that masking off, and it'll just put X's in the logs so you know something occurred, but nobody's going to get the credit card numbers out of mining that kind of data or the data traffic. Or you can encrypt it if you really need to see what the results are from a problem-solving perspective, and then use key pair encryption in the tuner to unpack those things to take a look at them. But that's a really big issue in a lot of data centers, especially in a public cloud, where you believe it's secure, but nothing is really secure these days. We all kind of understand that and live in the reality of that, and nobody wants to turn into Experian and all of your credit card information got made public somewhere in the world today. So marking things, the ability to mark that is really important. And I think I actually zoomed through this at hyper speed. So let me take some questions. Let you guys ask about the problems you've seen or the issues you've seen. And there's probably a couple of other points that I can toss out there that might be useful.
Anyone have any questions? If you raise your hand, I'll bring you the mic and we can.
You guys are quiet today. I need more coffee. So while you're thinking, one other point that we've learned in the virtualization world that I think is a very important consideration. Speech recognition servers, and especially, are probably the most computationally intensive piece of code you'll put in a data center. They make database servers look like slackers, essentially, because it's all real-time computation to do a recognition task. It's not I/O intensive in terms of the disk, but it's a lot of MIPS essentially of both CPU for the number of threads you're processing simultaneously and memory for each of those grammar images and the audio to be compared and modeled against. And it has to happen really quickly. So when your application says, you know, what kind of topping do you want on your pizza? And you say pepperoni and cheese, and that gets bundled up and sent over the network to the recognizer, you got about 200 milliseconds, maybe 300 milliseconds before you need an answer back in the application, or users will perceive latency and not like the user interface result. That's really quick by the time you count network time, sucking that stuff into memory, doing the search tree, and returning a result back in your application responding to that logic. The result of that is, if you look at the way hypervisors and virtual machines work, VMware clearly says in their documentation they can't give you in highly computationally intensive tasks resource switching that is fast enough to meet that demand. So if you deploy speech recognition servers in a virtual world, you absolutely need to configure the CPU and memory resources as reserved to the machine instances off of your physical host so that they're dedicated to the use of that virtual machine. And my personal recommendation from a lot of practice at this is think about the size of the virtual machines you have on a given physical host and don't oversubscribe the physical host. So if the cumulative reservations for memory and CPU on all of the logical machines on a given physical host are too large, the hypervisor can never stay caught up under sub 300 millisecond response times to polish those tasks and get them back to you quickly. So just take it from a lot of hard knocks and learning out in the world. You want to reserve memory and CPU for speech recognizers in a virtual environment, or at a minimum not oversubscribe the physical host. Questions, anybody?
All right, with that, let's give a big round of applause. I'm sure you'll be available afterwards if people would like.